Hi, and welcome to this introduction for my section of the chemistry of everyday things. I'm a photochemist and a spectroscopist by training, in that I use light to make chemical reactions happen, and I also study the reactions that are occurring using light to look at those molecules. Now, I'm sure you are all familiar with things like the Balmer series. So this is the line spectra of hydrogen, and it was noticed that the line spectra of hydrogen in the absorption and the emission completely overlay each other. And using this equation here, we could relate the frequency to particular quantum numbers within the transitions. And this is this idea that I can move between defined energy levels within molecules. Now, we're all familiar with this. We've all seen colours of fireworks. This has been something that's existed for hundreds of years. And it's transitions between particularly defined energy levels. So if I look at the electromagnetic spectrum, we have the bit in the middle we're all familiar with, the visible, but there is also X-rays and gamma rays at very high energy, very low wavelength. And then we have the UV region, which spectroscopically marries with the visible part. Infrared, microwave and radio waves, and these all match to different transitions within a molecule. So if I'm looking at X-rays and gamma rays, I'm looking at high energy transitions, so transitions between core electrons within a molecule, or I could be looking at transitions within the nucleus of a molecule. When I'm looking at the UV visible, I'm looking at valence electron transitions. Infrared looks at vibrations, microwave looks at rotations, and radio waves is normally used in NMR. But theoretically can also be used for translations and is in some astronomy purposes. Now, this is the basis of all spectroscopy, the fact that energy levels are defined. And you've seen this before when we've done thermodynamics, but I have my translational energy levels, which are closest together. My rotational energy levels are next closest together, followed by vibrational and electronic. And we've seen how those marry up to the different parts of the spectra. And it's transitions between them which are promoted by either absorption or emission of a photon. So if I'm having absorption of a photon, I'm moving up in energy. If I have emission of a photon, I am moving down in energy. And that is the basis of spectroscopy. So if I look at things like sodium, sodium streetlights used to be fairly ubiquitous. But I have numerous different transitions within sodium, and they're governed by what is called a selection rule. And the selection rule says that the angular momentum change can only be plus or minus 1. So, for example, I can go from 3s to 3p, or 3s to 4p, or 3s to 5p, but I can't go from 3s to 3d. It's just not allowed. And so I only have a particular number of transitions in the molecule, and they line up with this spectra beautifully. And if we look a little bit closer, we actually see there's a little bit of splitting. I can see that that bright yellow line of sodium is actually a pair of lines, and that's because I've got a little bit of extra detail here that I can look at more closely. And this means that we can really start to probe deeply how an atom or a molecule is looking depending on its spectra. So if I actually now look at molecules rather than atoms, I can have a similar thing. I can move between different energy levels, and this is me moving between pi bonding orbitals and pi star antibonding orbitals. And I can see as I increase this chain length of single bond double bond pattern, which is called conjugation, I increase the wavelength or decrease the energy gap between my ground and my first excited state. The same thing happens if I have a heteroatom, so if I've got atoms like oxygen or nitrogen, I now introduce non-bonding orbitals, and in this case I can have transitions between the pi and the pi star, or the n and the pi star orbitals. But again, I see the same pattern. The more of this pattern I have, the smaller the energy gap between them comes. Now we can see this in real life with this molecule here, methylene blue, and I can see my absorption spectra here has multiple peaks. This is allowing different absorption bands within my molecule. And it depends on the amount of conjugation I have in the molecule as to how much I see. And if I look up the side here, this is the molar extinction coefficient, which is plotted on the y-axis, and I can see that methylene blue has a relatively high volume of molar extinction coefficient at about 78,000 at its lambda max. Now, if I think about uses of light, one of the things that it's useful for is actually for doing the Beer-Lambert law, and you'll have all seen this in the labs by now, but here I have my log of my ratio of intensity of incident and excitant light, and that is my absorption of my sample, and that depends upon that molar extinction coefficient, which we've just seen with methylene blue, the concentration of the sample and the path length. If I increase my concentration of my sample, I increase the amount of absorption. If I increase the path length of my sample, I increase my amount of absorption, and it all depends on that molar extinction coefficient. coefficient. Now, we've seen for methylene blue, that's relatively big, 78,000, but in cases where my transitions are nominally disallowed, it's going to be much lower. And so if I look at octahedral complexes here, what happens is I have this 3D orbital, which is actually split into two energy levels because of the environment around that central atom. So this is coming from the molecules which are bonding to that central atom. And so if a titanium hexaaqua, it's those hexaaqua around the titanium which are giving me this split in energy levels, and the transition I see is from this T2G set to this EG set, which are all 3D orbitals, and therefore it's a DD transition and it is forbidden. And so my molar extinction coefficient for this transition is low, about 6. This is the same thing we see with copper sulfate. Copper sulfate we think of as blue, but the molar extinction coefficient for copper sulfate is only about 20 per molar per centimetre, so it's relatively low. Now, other things that I have are emission of light, and we have fluorescence and phosphorescence, and I'm just using fluorescence here in as an example just to show you that we see the fluorescence spectrum being a mirror image of my absorption. So on my left I have absorption, on my right I have fluorescence, and this is of this molecule YoPro1, just any old molecule that I have chosen to show you, but I can see it's still got that pattern of single bond, double bond conjugation that we saw earlier. Now, why do we have this mirror image? Well, it's because it's going between these two levels, the S1 and the S0, absorption on one side, emission on the other. But unlike in the case of my gas phase atoms, I have a solvent shell around these, and it's the solvent shell and the molecule structure which is able to change. I've got a more complicated system, and so they don't overlap perfectly in the case of fluorescence and phosphorescence. I have this slight offset between the two things. Now, it's not just absorption and emission, but I can also see scattering of light. Scattering of light is what gives us our blue skies or our red sunsets, all of these different things, and blue and red light are scattered by different amounts. Blue light is scattered more than red light, and so we actually see this phenomena when we see a sunset. Red light is scattered less, and so when the sun is lower on the horizon, I see the less scattered red light, the blue light is scattered away. So you're well used to these things, but these are all things to do with the energy levels within molecules. Scattering is less so, but we're going to see a case of scattering now where we call it inelastic scattering of light. And again, I'm back to my my transitions within my molecules. This is called Raman scattering. Now I can see Raman scattering in both rotational and vibrational energy levels, and it's a well-used spectroscopy nowadays. So this well-used spectroscopy is using these energy levels within a molecule, but I haven't actually got absorption or emission. I have scattering of a photon. So we can play this game slightly differently as well. Now, this has been a brief whistle-stop tour of light, and I get that not everybody is passionate about light and why light interacts with molecules as I am, but why do we care? Well, we care because actually colour is the foundation of the whole of the chemical industry. William Perkin was the founder of modern chemistry, and he did it by making the first synthetic dye movine. It was a beautiful pink colour. If you ever see the medal of the President of the Royal Society of Chemistry, it is on a pink movine ribbon. It is that important to us as chemists. And it was because he synthesized these dyes that we have the chemical industry that we know today. So colour matters to everybody, whether you get excited about absorption, emission and scattering the way that I do, or whether you are just interested in basic chemistry. Now, the basis of this course is very much over to you. I'm bringing in people who use light in their work, but I want you to be involved in that. And so I want you to start to think about questions that you might ask people, whether it's myself or any of the people that I'm going to bring on board into the panels, but I'm going to share some of their work with you first. And you're going to see the range of things that you can do with light and why it excites me so much. I look forward to seeing you in the Loyals.